This session of mathematics physics this afternoon have 3 speakers. Together they cover a very wide range of topics. So there will be an exciting afternoon. The first speaker is a local boy that comes from Seoul National University. So Seung Yeal is going to talk about collective dynamics of interacting many body systems, Lyapunov functional approach. Professor Ha.
Okay, so thank you for introduction, and also as a local boy, I have a big advantage to have this Korean audience a lot. Okay. So I'm going to tell you some story about the collective dynamics of some interacting many body systems using the so-called the Lyapunov functional approach. So here is a brief outline of my talk. So I'm going to give you some motivation why this topic might be interesting for you. And then I'll give you some roadmap of my talk and talk about this Kukusme flocking and some application of the flocking and the synchronization and the quantum synchronization. And then I'll summarize my talk. Okay, so I just prepared some pictures and movies for your understanding. So as you might agree, all humans have a dream to fly like a bird or run as fast as cheetah, right? So this dream was realized more than 100 years ago by Benz and Wright brothers, and we even have more ambitious dream to make driverless vehicles, so-called unmanned aerial vehicles. So if you have one single driverless vehicles, then you have to control, okay, to have a mission completed, okay. However, if you have more than one, say you have several unmanned aerial vehicle or robots, then you might have a chance that you don't need to control centralized, but you can control using the decentralized control, so they can talk each other to have a mission. So, right. So the question is, from a control theory viewpoint, design some efficient decentralized control protocol for multi-agent system for this multi-agent robot and unmanned aerial vehicles. So the IEEE control theory community organized big meeting, so-called CDC meeting, conference on decision and control every year. So all from 2000, this decentralized control algorithm and the flocking and synchronization is kind of an active research area in control theory. Okay, so the question is how to make such decentralized control. So we just listened to the message from Poincaré. He died 100 years ago. Actually, he died in 1912. So he tells us, go back to the nature. So nature not only suggests to us the problems, she suggests the solution, okay? So the question is, go back to nature. Okay, so let's go back to nature. So I'll show you some movies that I downloaded from YouTube. So you can see the left movie is the so-called bird flocking. The right movie is called the rolling phenomenon or swarming of fish. So you can see this kind of natural phenomena. So, so the flocking basically is alignment of the velocities. So you have this interacting particle system. Then when I say flocking means they align their velocity together, so they move together. Now, we have another example of so-called the synchronization. So the left movie is the flashing of fireflies. The right movie is the synchronization of the metronome. So this periodic interacting oscillatory system, sometimes they adjust their rhythms. So you'll see some movie later. Okay, let's see what happened. Already the left movie shows you some synchrony. Okay. Oh, right. So this kind of adjustment rhythms are called synchronization. Okay. So today I'm going to show you some models, some mathematical models showing the flocking and synchronization. From the classical system, I'll show you Cosme model and Kramoto model, and the quantum system, so-called the Rohe model and Schrödinger-Rohe models. Okay, so I show you these 4 models in my talk, and so the question that I'm going to address is, do these models describe the collective behaviors? Okay, unfortunately, these models are derived phenomenologically. Are not derived from the first principle of physics. So you have to know under what condition these models exhibit collective behaviors. And also I'll show you some relationship between these 4 models and raise some open problems you might be interested in. Okay, so in the title I show you is subtitle is the Lyapunov function approach. So I'll tell you who is the Lyapunov. So Lyapunov actually is the first, actually is the godfather of dynamical system in Russia, maybe in the world. So in 1892, he published his thesis, so-called the general problem of stability of motion. So in this thesis, he proposed the concept of stability. So we call the Lyapunov stability and asymptotic stability, and also he showed 2 methods, so-called the first and second method. So I'm interested in the second method. So I show you, I just briefly tell you what the second method is. Suppose we have the ODE system, okay? Then we look for the so-called equilibrium solution, which is the solution of this f of u equals 0, okay? Then asymptotic stability means if you choose any initial data is close to this equilibrium, then we want to show that asymptotically the solution trajectory of the solution approach to this equilibrium, okay? That is called asymptotic stability. All right. So then the typical Lyapunov theorem tells you, suppose we can find some C1 function defined on some open set containing this equilibrium point, such that V is positive definite. So that means V is always a non-negative, and equal to 0 means V exactly at u sub e. And the orbital derivative, which means you evaluate of V along the solution and take time derivative, is a negative definite, then Lyapunov theorem tells you u sub e is asymptotically stable. Okay? No linearization, so it is called direct method. So the question is, suppose if we don't have equilibrium a priori, okay? Because if this theorem tells you, at first you have to have equilibrium first. But suppose we don't have equilibrium, then what can you say about the existence of equilibrium and stability of this equilibrium? So I'm asking the emergence of equilibria and its stability at the same time. Okay, so that's the main theme, main question of my talk. Okay, so let's move on. So the first model that I will show you, so-called the Kuko-Smale model for flocking. So the Kuko-Smale model was proposed by two mathematicians, Cooker and Seung Yeal. You know the Seung Yeal. So xi vi is the position and the velocity of some ice particle. Then the time derivative of position is the velocity, and mass times acceleration is the force. So they choose force as this kind of a weighted average of the relative velocity. Okay, and then in particular they choose this weight as this algebraic way. So why this system can give you the flocking? Okay, so for example, if you look at its component, or let's say in one-dimensional case, so the particle move on the line, then your neighbor's velocity is larger than your velocity, then you have to accelerate to have a flocking, right? Because your neighbor is faster than you, you have to accelerate. Reversely, if your neighbor is slower than you, then you have to decelerate. Okay, so this kind of attracting force already hidden in this forcing mechanism. Okay, so right. So then the question is whether this model is physical or not. Of course, it's not physical. It's not derived from the first principle of physics, or not derived from some Lagrangian variation formulation as well. So therefore, we have to ask. Okay, so as a simple motivation, we consider one-dimensional particle system on the line, and again, the p prime. So let's say each particle interact in the mean field way. That means all particles interacting each other, not near its neighbor interaction. So, and then we add a linear damping. Okay, so the only empirical or phenomenological component is just adding the linear damping here. M is the mass. Okay, so somehow this model can be acceptable as a mechanical model. So okay. Now, let's take the time derivative of second equation. Okay. Don't ask why. I just take time derivative. I don't know what to do, so just take time derivative. So if you take time derivative of the second equation here, this forcing equation, then you have this one by chain law, chain law, right? Now I let n goes to 0. So the small mass limit, consider small mass limit. So then formally, you can delete this guy, and this guy move here, then you cover the Cooper-Seung model. Okay? So in that sense, Cooper-Seung model is not so bad. Of course, you might ask, this is a singular limit. However, this you can, if you use the Tikhonov theorem directly, you can justify this formal limit rigorously. That has been done in these two papers. Okay. Now, okay, so I want to show this Cooper-Seung model exhibit so-called flocking phenomena. So that I have to define what the flocking is. So, if we have an interacting particle system with position and velocity, I simply define the flocking asymptotic sense means the relative position is uniformly bounded, so you have a group, and also the velocity asymptotically aligned. That means the relative velocity goes to 0. Okay, that I call the flocking. Okay, that makes sense. Okay, so then how the Cooper and Seung Yeal prove this flocking for his model. So in particular, they choose this psi, which is the communication weight over here. Okay, so weight. When you add the relative velocity, they choose the weight. So if the relative distance is far away, the weight is small. The relative distance is small, then weight is large. Okay, that also makes sense, right? If you're far away, then it's this effect of communication is small, and so on. So what they prove, is if the decay 2 beta less than 1, that means it decays slowly, then you don't need any condition on initial configuration to guarantee the asymptotic flocking. However, if 2 beta is greater than or equal to 1, that means it decays faster. Even if they all particles talk each other too far away, but the decay rate is so small, then you need a condition on initial configuration. So this conditional flocking. So this model, they use kind of L2 norm. So the n dependence, because the region depends on n, they also use the spatial psi. And this Kupper's work has been generalized many people up to here. Then I want to generalize Kupper's so that you don't need a restriction on n. So n independent proof the region, and also I want to allow spatial psi, okay, not algebraically decaying. You may allow exponentially decaying, etc. So here's the theorem. So if you define here, I just assume that total position, the sum of xi, sum of vi equal to 0. Then I just look at the variation, and in L infinity norm, this is L2 norm, but in index you take a maximum norm, so it's L infinity norm. So what you can prove, if initial data and the communication weight satisfy this inequality, then you can prove that the spatial fluctuation is uniformly bounded and the velocity fluctuation goes to 0 exponentially fast. So the good thing is, you don't need, there's no n here, okay? So of course in the model we already scale out n, we divide it by n. So this region is independent of n. So you can lift this region to the other kinetic or fluid regime. And also somehow we allow the general psi as long as it's Lipschitz continuous and non-increasing in the argument, etc. So of course there's preliminary work for this kind of things before. And what's the improvement of this result is, for example, 2 beta equal to 1. So that means psi basically decay like 1 over r, like Coulomb potential. In that case, the Foucault-Smith result, you have a conditional result, restriction on initial configuration. However, this result, psi is 1 over s, this is infinity. So you don't need any condition. So in that sense, somehow this result the critical case. Okay. So the proof, we use the so-called Lyapunov type functional approach. Okay. So that's why the crucial component of this talk is the Lyapunov function. So the art of this Lyapunov approach is to design this kind of function, okay? Because it depends on the system, and also sometimes you need the trial and error to construct. So still we have some open questions. So because so far I'm talking about the so-called global flocking, everybody flock in as a one group, but if this condition is violated, then at the numeric simulation you may have several multi-flocking. Okay. However, so far there is no analytic proof for such a emergence of the multi-clusters, and also at the more engineering level or physical level, if you have a finite range communication, because if you are too far away, you don't talk. You just talk nearby, right? So in that case, so suppose you have the relative distance is less than r, then you have a 1, otherwise 0. So this finite range communication, how can you prove the emergence of flocking for non-trivial initial configuration? Okay. This looks trivial, but I know the control theorists that last more than 10 years, they are struggling still. Okay, so however, if the number of particles is sufficiently large, then we can approximate this particle system by using the kinetic equation and these fluid type equations. Okay, so when n goes to infinity, somehow you can prove the solution of this guy converges to solution of this kinetic equation. That has been done rigorously in these papers. And for the Lyapunov of this kinetic equation is not that hard, so you can prove any good theorem for Lyapunov for classical solution or weak solution, etc. Even measure value solution. And also from this kinetic Foucault-Smale model, if you take the first moment, second moment, then this quantity formally satisfies this balance law. You have balance law, and then the source involves with its non-local forcing term. Okay. Unfortunately, so far we don't have a good closure condition for this one. However, if the agent group is close to flocking state, okay, you can close to flocking state, then you can employ so-called monokinetic ansatz for this density function f. So if you substitute this ansatz to the this stress tensor and the heat flux, they are all gone. Okay. So you have this so-called pressureless gas dynamics with this non-local flocking forcing term. So if the coupling stress K is 0, this pressureless gas dynamics has been studied a lot in maybe more than 15 years ago in the French group and the Beijing group. In particular, as a simple case, when psi equal to 1, so-called all-to-all case, this equation, this system reduced to pressureless gas dynamics with damping. Okay, so last year, this Fei-Mi Huang, Wang Yi, we could prove the 1D weak entropy solution for this case, and also my former student Moon Jin Kang and Bong Seok Kwan, we could prove the classical the solution of prove the existence of classical solutions on a torus and a whole space. Of course, it's with a compact support, so it's in the domain is compact on a bounded set. And also you can, so far we just look at the particle system, but in reality the particle system interact with the fluid, right? Air or water, etc. So the coupling between the kinetic Foucault-Smale with various fluid type models has been done actually with Hyung-Ok Bae and my former student. Okay, so we did many things on this, but actually our modeling somehow motivated by this modeling of thin spray by Deblet group in France. All right. So what I'm gonna do with this mathematical region? Okay. Of course, I'm not the real engineer, so I'm not going to make a unmanned air vehicle, etc. But you can think of at least you can think of the formation of this air show by unmanned aerial vehicles. Okay, I know nobody did, but so in principle we can do it. So with this have in mind, I work with engineers actually from Seoul National University. So this is Foucault-Smale model. We added some bonding force over here. Looks complicated, but this forcing mechanism was motivated by the physical argument. Okay, it's not just added ad hocly. It's just somehow we use the physical motivation. So in 4 particles, you have this formation control, etc. You can prove some theorems on it. And also, I want to apply this flocking idea to sociology, why this rich group and the middle class and lower group appear in our society. So that's the motivation of our work with Kyung-Keun Kang and Jung-Han Kang from Yonsei University. He's a sociologist. He's in the Department of Sociology at Yonsei University. So from why this culture class emerged from assimilation and distinction, etc. So that's some work. And also we try to apply this flocking idea in the financial domain. So our first trial was for the credit market. And also later we applied this flocking idea to the modeling of stochastic volatility with the financial researchers in Aug University. So two of them are here. So we try to somehow use this flocking idea to model various social and phenomena. Okay, so now I'll go back to the second model, so-called the synchronization, the model for synchronization. Okay, so if you, for example, if you start from this so-called Stewart-Landau oscillator, whose its dynamics is governed by this ODE, Z is the complex valued function, so you can always rewrite Z as a polar coordinate. Then if you substitute these answers to here and separate the imaginary and real part, you will have this. Here's omega, note J here, omega, capital omega. So you see that this omega is the natural frequency. It's a frequency or a phase velocity. And also from this equation, you can see that R equals 0, R equals 1 are the equilibrium, but R equals 0 is unstable, R equals 1 is stable equilibrium. So it's a unit circle, it's a limit cycle, stable limit cycle. And so the oscillator, this oscillator is called Stewart-Landau oscillator. So now I want to couple these oscillators in the linear way. Okay, so you add this linear relaxation time. Then because I'm interested in the limit cycle, so we know the unit circle is the limit cycle, so you can rewrite ZZ as a polar coordinate. You plug these answers to this coupled system, and then compare the imaginary part, then you'll have a so-called chromatin model. Looks so simple. We have just sign coupling. K is the strength of coupling strength. Omega I is the natural frequency. N is the number of oscillators. So this model was proposed in 1975, but still, after 40 years later, now still many researchers in statistical physics, engineers, mathematicians are working on it. Still, we don't know much. That's irony. So simple, but we don't know much. So this chromatin model has two components. So you have a random component, okay? So and the nonlinear coupling. So the coupling strength is 0. There's no coupling. Then the phase velocity just is given from somewhere. Okay. So for two oscillator system, if you consider this difference, this chromatin model reduced to so-called the Adler equation. This equation, you have explicit solution. And also you can notice that when K is greater than F's value of omega, this guy has an equilibrium solution, stable equilibrium solution. So to have a stable equilibrium solution, you need to have a condition on this nonlinear coupling strength. Okay, what about n greater equal to 3? I don't know how to do it. When I when I made this equation, like maybe December 2007, I didn't know how to do for a year. Let me show you some numeric simulation done by Jin-Young Park, my current student here. So the left-hand side, we did a 50 oscillator. The natural frequency is a random variables extracted from this uniform interval. This is k equals 0.8. This k is 2.2. So if k is small, you don't have a synchronization, but k is large, you can see the synchronization, right? So the question is how to prove it. This is numeric simulation region. Okay, so here's the problem statement. For given generic initial phase configuration and sufficient large k, we want to show that the relative phase velocity goes to zero asymptotically. This kind of question has been addressed by the engineers in the beginning, like 2004, but at that time, there were a lot of restriction on the initial configurations. And 2009, February, just before the earthquake in L'Aquila. L'Aquila earthquake was April. So 2 months before, I was visiting University of L'Aquila. L'Aquila is a small city. Total population is 68,000. The number of students is 20,000. And so the person who involved in the university is more than half of the city, the population. So a small country, a small city, no bus on the weekend, maybe one bus every 1 hour. So I was, most of the time on Sunday, I was in the hotel. I was thinking about the promoter. And then I found some idea. Idea is so simple. Because I told you, you don't know what to do, just take derivative. So you have a first order equation. I define zeta I equal to omega I. I take a derivative of this guy. So this is constant, time independent. So omega I dot, this is gone, k over n, sine becomes cosine, and this guy becomes omega j minus omega. So if once you write down this first order system as the second order system, then you see something, right? It's close to, it's like a Krukos-Smell model. I know what to do for Krukos-Smell model, so I begin to apply the methodology that I know for Krukos-Smell to the problem. So, our first trial was done in this paper. Later on, what we proved with my former student, if the initial phase diameter is less than pi, that means initially the oscillators are located in the half circle, the diameter of natural frequency positive, coupling strength is larger than this, then you can show that the frequency diameter goes to zero exponentially fast. So this tells you asymptotic synchronization. Okay? So I have 10 minutes, so I will accelerate, okay, to finish on time. So the proof, again, based on these two Lyapunov functional and the Grunwald type inequality. And just recently, Hwa-Gil Kim here and Seung Yeal, we can get rid of, we can prove the complete synchronization for generic initial configuration. Okay, so here is the initial, this quantity is strictly positive, initial phase are different, and the natural frequencies are bounded. Then you can find for some large coupling strength, so then if coupling strength is larger than this guy is explicitly computable. then your configuration converges to some phase-locked state. Okay, so that's the statement. I don't know whether I have time, but it's so basically the idea is we use the gradient flow structure of the parameter model together with the explicit information for the identical oscillators. Okay, so maybe I just skip the proof because I don't have much time. Okay, so there are several ingredients in the proof. So now let me just move to this quantum synchronization. So far, I only talk about the classical system, right? You have a position, the velocity are well defined, phase are well defined, but let's just imagine you have a quantum oscillators, quantum network. Each node at the oscillator are sitting there, but this oscillator is quantum object. So it might have several states with a certain probability, right? Now your phase is the state. It's not just one single state. You have many states. So then you might ask, how can we synchronize those quantum oscillators? I don't have to figure out the model. Actually, the physicist Max Lohe proposed the following models in 2009 here. UI is the D by D unitary matrix. UI dagger is Hermitian conjugate. HI is the Hermitian matrix, etc. So and then of course I knew this model around this time actually because I was interested, but I could not read the paper. This the algebra, group, whatever. I don't know anything about that, so I just keep it. And then I asked Professor Dongpyo-ji over there. So he thanks to his help, I could understand the model. So for simple case, for example, one-dimensional case, 1 by 1 Hermitian matrix, just the complex number with the modulus 1. So you can rewrite as a polar coordinate. 1 by 1 Hermitian matrix is just real number, right? So if you substitute these answers to the previous system here, then it just reduces the parameter model. Okay. Of course, this is one generalization of parameter model. And also, if you switch off the coupling strength K in the Lohe model, you multiply UI to the right-hand side, then you get the usual Schrödinger equation with a finite state. Okay? So this Lohe model is a generalization of the parameter and Schrödinger model. Okay? So you can ask the same question that I told you. So you have two matrices, and then I want to show that asymptotically the relative distance between these two matrices goes to constant state. Unfortunately, I don't know how to deal with this matrix valued ODE system. So in general, I don't have an answer. But for special case, 2 by 2 case, which corresponds to quantum-based system, cubic system in quantum information, in that case, this 2 by 2 unitary matrix can be written as a linear combination of Pauli matrices, like here. So somehow you can rewrite matrix value ODE system as this vector valued ODE system, which I know how to deal with. So you clearly see the shadow of the parameter model is built in here. So in that case, again, under some condition on initial phase and initial position, you can prove this is diameter in the phase, and the diameter in the position, just Euclidean distance, goes to zero exponentially fast. Okay, Of course, this result was later improved by using this order parameter approach, but I'm not going to talk about that today. So again, the idea is to use this Lyapunov functionals and together with the Gronite type inequalities. And also, so far, the previous one, you have only finite state. You can generalize to the infinite state quantum system, like Schrödinger equation. So you have this for Schrödinger and Loe model for identical oscillators. So you have this free Schrödinger equation, and you have a Loe system, and the solution operator isometry. So by using that property, again, you can define this Lyapunov functional as a diameter between the state functions, and this you can, under some condition on initial configuration in K, you can show that this diameter goes to 0 exponentially fast. Of course, so far this result is not optimal. There is still room for improvement, but this is, and in any case, this is first analytic result for that. Okay, so let me summarize. Okay, so we have discussed the unified approach based on the Lyapunov functional for this flocking and synchronization, even for classical system and quantum system. And as you clearly can see that we still are not complete, okay, in the understanding. Still, there are lots of open questions out there. Okay, so thank you for your attention.
Okay, thank you, Professor Ha.
Yeah, I counted my collaborators, 31 collaborators so far in the last 7 years. Some of them are economists. For example, Jane Yu, she's an economist. And we have engineers here. We also the financial expert or financial engineers, etc.
Any politician?
So far, yeah, but actually, I'm talking to the politician, former politician.
Okay. Well, thank you, Professor Ha, for this beautiful talk. We open for question and comment. But before that, and before I forgot it, the organizer has a present for the speaker. Okay, so questions? Yes.
Thank you for your very nice talk. And when you apply your models to social or economic financial problems,
Yeah.
What do you control in your equation?
Because the original Focus-Mann model, we only count for the attractive force, okay? Because we want to have one group. But if you have a multi-group, then somehow you have to add a repulsion force. So we call the dissimulation. So somehow we add, of course, we propose two models for that mechanism, but the attractive force and repulsive force are present there at the same time. Okay? So why? Because if the poor people want to somehow imitate the rich people, then rich people want to avoid, right? So that's why you have lots of, in Korean, called jaga. Fake. Okay, so and so on. So that's the basic idea. And so it's a repulsion and attraction.
Yes.
First, I'd like to thank you for a great talk.
Thank you.
You derive the condition for the stable synchronization of
Yes.
the model. I wonder, is it possible to derive the frequency of the synchronization in the model?
Okay, so right. So of course, because in the, say for example, the parameter model, all the phase collapse to one point. I call the complete phase synchronization. All the frequency collapse to one value, we call complete frequency synchronization. So I talked about both. But now your question is frequency has its own dynamics, like inertia. If you add inertia, actually we did that case as well. But although I didn't talk about here with Seok-bae Yoon, Professor Yoon there, and Young-pil Choi, there is a work, yeah.
Yes.
On the pressureless Euler model with relaxation, there is a very nice paper by Paolo Antonelli and Piero Maccati where they get almost that model, but they have a pressure in it.
Oh, yeah.
And they derive it from quantum mechanics.
I see.
Okay, so they start from a Schrödinger equation with a pressure, so with a nonlinearity in it, and then they prove that in some limit, in the semi-classical limit, they get precisely that problem. So I wonder whether you could sort of go backwards with a pressureless model and write down a linear Schrödinger equation with, now maybe it won't be linear, but I mean it won't have a pressure term in it, and sort of prove a theorem then for the Schrödinger equation. That would be interesting.
I see. I didn't know that reference. Okay, that's a good question. Yeah, sure. Thank you.
More problems, more future. That's good. All right. Yes.
My question is about the Kurzweil model, which you showed first. So, while defining the group formation, you added up the magnitude of the distance difference between different particles. So, do you ever get the situation when the distance shrink to zero and you have a very trivial system where it moves like just one particle?
Even this like a sticky particle.
Like every, since there is no volume of these objects, right, of these particles.
Right.
Is there any situation or conditions in the initial data where everything shrinks to one point and then everything moves with the constant velocity?
Okay.
Any kind of similarity.
Can I go back to my slide? Yeah. So that's So for the Kurzweil model, whether this total collapse, is possible or not, I don't know. I don't have thought about. I haven't thought about that. However, I told you some Kurzweil with a bonding force for this formation control, because basically we want to have a collision. Although the particle is sitting in the center of this ball, somehow the radius of R is the kind of like the shoot. Okay, so for this model, whether the total collapse is possible or not, or collision is possible or not, actually with Dr. Hori and my former students, we studied under certain initial configuration, even collision can be avoided for this model. So the total collapse is impossible for this model. But the Kurzweil model, total collapse, I haven't thought about it, but it may not be possible. That feeling.
Yes, I thought maybe if the interaction or attraction is too strong, they could just align everything at one time.
But this Kurzweil model already is exponentially synchronized. So unless your special configuration is spread out, maybe total collapse can be avoided.
Maybe one more question. Okay. Thank you very much.